Okay, good morning. This is Tuesday, March 31st. This is going to be the next installment of lessons. What I would like for you to do is take notes. A couple of things that I'm including with this one is I'm going to include some worksheets that we'll do at the end. I'm also going to include some practice problems from the previous material with dealing with light calculations and energy calculations, just for you to have some extra practice. But today we're going to start looking at electron configurations. Now, this is not that difficult. I'm going to try to make sure I cover it all. I will also post a crash course video that talks about electron configurations and things like that. You will need to have a periodic table today. That's going to be very important because in order to do these, you have to be able to apply it to the periodic table. So things that we're going to need today, or things that we're going to try to accomplish in this lesson today, is first be able to list the total number of electrons needed to fully occupy each main energy level. We should be able to state the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Not only state them, but also apply them to electron configurations. Electron configurations are not difficult. They just require you to think a little bit and to count a little bit. So again, and we're going to apply these rules. All right. Describe the electron configurations for the atom of any element using orbital notation, electron configuration notation, and when appropriate, noble gas notation. Under these, there's going to be two types. There's going to be regular order and expected order. We are primarily going to focus on the regular order notations. Again, these are not hard. It's just something that's just something that we need to be able to do, and be able to do and recognize. I am going to put another short video that talks about quantum numbers, but they're not as important. But it'll just be a short, brief video about that. But because there are a couple of questions that we have to answer based off of those. All right, up until this point, we have discussed the shape of an atom in terms of a Bohr model and the electron cloud model. In the past, you've always done it as the Bohr model, where you have a nucleus. Let me get a color that actually marks on here. You would have a nucleus. Inside the nucleus, you're going to have protons and neutrons. So let's just say we were doing carbon. Carbon has 6 protons, and if it's carbon 12, it's going to have 6 neutrons. We also know that carbon a neutral atom of carbon will have 6 electrons that we have to keep and accounted for. All right. So in physical science and 7th and 8th grade science, you probably learned that we look at the row that carbon is in. Carbon's in the second row, so that means it has 2 energy levels. All right. On that first energy level, we can hold 2 electrons. And so since we're trying to accomplish 6, that means that we need 4 in the second energy level. All right. Now, what we're going to be starting to do today is show how to count these electrons in a little bit different way. Rather than having to draw out the picture, we're going to number these in a different way. So one of the things that we've learned is that electrons don't travel around the nucleus of an atom in orbits. So Bohr model is technically wrong in this. What we found is that they travel at different distances away from the nucleus. So the way that this model is right, it shows that these electrons are a fixed distance away from the nucleus, and these electrons have a certain amount of energy that cause them to be a fixed difference away from the nucleus. But what we're going to start doing is, rather than refer to the electrons in energy levels like this, we would say that carbon has a quantum level of 2 because it's in the second period. But what we're going to start showing is that in the first energy level, it has a particular shape called S, which I'll talk about that in a few minutes, and there's 2 electrons in it. And in the second energy level, it has an s orbital that has 2 electrons, and this orbital can only hold 2 electrons maximum. So we have to account for these other 2 electrons, and that it's in the second energy level and has a p with 2 electrons. So we have 2 plus 2 plus 2, and that gives us 6 total electrons. All right, so I know this is probably not making sense just yet, but what we're going to see is, as we progress through this, we're going to see different ways to show this, and it will start making sense as we go through it. We're going to be talking about different things like spin, direction of the electrons. We'll talk about filling the lowest energy level to the highest energy level. So some of the things that we need to know is the lowest energy level is going to be the closest to the nucleus. And as we move away from the nucleus, the energy level gets higher. So again, as we move away from the nucleus, it becomes higher energy. All right. So let's go ahead and start looking at some of the shapes and some of the things like that so that we can kind of get into this. All right. All right. So just kind of continuing on, electrons cannot exist in between energy levels, so they have to be at certain energy levels. We call those energy levels principal quantum numbers. All right. And it indicates the size. So N indicates the relative size and energy of the orbitals. N specifies the atom's major energy levels, called the principal energy level. And so if you're looking at the periodic table, you might notice that we have 7 rows. So we have 7 energy levels. So we have N1, N2, N3, N4, N5, N6, N7. So these are our principal energy levels. These are our quantum levels. All right. There are 7 of them total. Each one can hold a certain amount of electrons. The maximum amount of electrons that can be held in N1 is 2. In N2, we can have up to 8. In N3, we can have 8 or 18 if it's an inner level. All right. N4, and I'm only going to do up to N4 for right now, but we can have 8, 18, and hold on just a second. or we can actually go up to 32 on this energy level. And I'll explain how that works as we move on. Now, again, we can continue on with these, and we're going to find a trend um, that occurs more and more as we go through this. So let me just, I changed my mind. Let's go ahead and finish this. All right, so N5 can contain 8 if it's the outer shell. If it's an inner shell, it could have 18, or it could have 32. Now, it can have numbers in between these as well. It just depends on what's surrounding it and what element it actually is, how many total electrons and all. Now, when we go to period 6 can have 8 or 18, and period 7 can have 8 or 18. All right. So just know that these numbers kind of shift depending on what's actually happening. And I need to fix something on number 7. Um, period 7 will have a maximum of 8. So we do see this trend that it goes 8, 8, 18, 8, 18, 32, 8, 18, 32, 8, 18, and then 8. And that's going to, again, this is the maximum number. So this would represent if we're talking about the noble gas for each one. So an example of N1 noble gas would be helium. If you're looking at a periodic table going down, the N2 noble gas would be neon. Neon has 10 electrons. Argon has 18 electrons. So that's the N3. Krypton has 36 electrons. Let me check my math here. Hold on a second. I think I did something wrong. No. Sorry. Um, sorry, we're looking at total number of electrons, but so krypton has 36 electrons. In its first shell, it has 2. In its second shell, it has 8. In its third shell, it's going to have 18. And then in its outer shell, it'll have 8, and that gives us the 36 total. And so as you move down the periodic table, you can see those patterns, and it will follow sort of this sequence. So, so let's go ahead and start getting into some of these examples. I'm probably going to confuse you at this point, but let us get into them. All right, so let's look at the shapes that we have here. So this first drawing represents the shape of, we call this the S. S is denoted as that it looks like a sphere. It can hold 2 electrons in this shape. It only has one orientation or one direction that it goes. And then along with the orientation, it has one thing, and it occurs in all quantum levels. So it occurs from N1 through N7. All right. Moving on to the second shape. The second shape is called the p orbital. We refer to the p orbital, we can call it a peanut because it kind of makes a peanut shape, or we call it a dumbbell. All right. In this one, I'm going to start in a little bit different place. It has 3 orientations. So we can have PX, py or pz is our orientations. Each orientation can hold 2 electrons. So we have 2 electrons times 3 orientations can give us a total of 6 electrons maximum. All right. Now, so in this one, both of these pictures are representing the PZ. The PX would be along that axis. The PY would be along that axis. All right. In this next one, this is called D orbital. It's the shape that we give it is called a double peanut. Now, these aren't true scientific words as far as the shape. It's just what we kind of attribute to it, and we do these to help you remember the letter designation D, P, and S. In this one, there are 5 orientations, and notice here that it says D, Y, Z. I'm not going to go into what we call each one, but notice that it is in the Z plane, but it is also going along the y-axis. So that's one orientation. Another orientation could be D XY, where it's laying flat like this. We could have D XZ, where it's moving along this plane. And we can have DXY, where it's moving along another plane. So, sorry, XZ, where it's standing up like that. So in this one, there are 5 orientations. Each orientation can hold 2 electrons. So that means if we have 5 orientations, it can have 10 electrons maximum. All right. So 2 electrons for each orientation. Now, the last orientation is called F. All right. Again, the shape that we kind of call it, it looks a little bit like a flower. There are 7 orientations for it. So that means that if each orientation can hold 2 electrons, that gives us a maximum of 14 electrons that can be held in that orbital. So energy levels are broken into sublevels. There are at least 4 possible types of sublevels, and they're given the labels S, P, D, or F. All right, so looking at this in a different way. So this would, so somewhere around here we would have our nucleus. All right, so if we're looking at this and we have our nucleus, and these represents our quantum levels N1, N2, N3, N4. All right, so in N1 we can only have an s orbital. Remember, an s orbital only holds 2 electrons. So when we look at elements like hydrogen and helium, the maximum number of electrons hydrogen and helium can have is 2. Now, we come to N2, we can have an S, which holds 2, and we can have a P, which holds 6. So 2 plus 6 gives us 8. All right. In N3, we have an S, we have a P, and we have a D. So 2 plus 6 is 8, plus 10 is 18. That's where we get the maximum number of 18. And then in N4, we actually can have an S, a P, an F, and a D. So 18 plus 14 gives us the 32. total. All right. So again, this is kind of how they're divided, and the pattern just goes on and repeats. All right. Um, so there are three rules that kind of govern or control how we fill these or how we create these things. The first rule you need to know is what's called the Aufbau principle. An Aufbau principle tells us that an electron occupies the lowest energy orbital that can receive it. So another way to say this is that we have to fill lower energy levels first, or fill low to high. So you start with N1 and fill in order N2, N3, N4, N5, N6, and 7. All right. So you fill from the innermost energy levels to the outermost. All right. According to so the next one is called Pauli exclusion principle. Pauli exclusion principle, in the textbook, it says no two electrons can have the same set of 4 quantum numbers. Basically, every electron has its own identity. This is what I'm going to give you a supplemental video that talks about this. We have these things where we say N, L, M, and so on. I'm going to talk about what those letters mean and all of that, but you don't need to know that to be able to do a orbital notation or an electron configuration. The big thing that I want you to know about Pauli exclusion principle is electrons in the same orbital must spin in opposite directions. So electrons that occupy the same orbital must spin in opposite directions. So when we start doing orbital diagrams and we have an individual orbital, we're going to have one electron that's spinning in one direction, and we're going to designate the other one with a down arrow. This is also represented by a plus and minus sometimes, but again, that's going to be when we talk about this type of information. All right, so I will present that on a separate video that's going to be much shorter. I just want you to see some things and understand some things. All right, moving on. According to Hund's rule, all right, Hund's rule is the third guiding rule. And it says orbitals of equal energy are occupied by one electron before any orbital is occupied by a second electron. And all electrons in a singly occupied orbital must have the same spin state. All right, so I'm going to draw something here, and it's not going to make much sense to you yet. But if we're talking about an atom that has a P. So again, let's look at oxygen. All right. So I'm going to give you the electron configuration for oxygen real quick. Oxygen has 1s2, 2s2, 2p, 1, 2, 3, 4, 2p4. All right. So relating this to what's called an orbital diagram, so I'm going to take each of these numbers and I'm going to show you an orbital diagram for this. All right, so we have the 1s, and that means it has an electron up and down. So according to Aufbau, I'm going to fill the lowest energy level first. So that's my lowest energy level. Then I'll fill the next level, which is 2s. Remember, S only has one orientation, so we have one blank for it. And so I'm going to fill it that way. And then I come to this 2p. And if you recall from the previous slide, P has 3 orientations. All right. Now, I have 4 electrons. So I'm going to follow Hund's rule. So all of these are equal energy. And so they're going to be occupied by one electron first, and they're all going to be spinning the same direction. All right, now that's 3. And so my fourth one, I'm going to come in and I'm going to fill it in here. So we fill up, 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 then down. So basically another way to say this one for Hund's rule is you fill your ups before you fill your downs. This really only applies when we're doing orbital notation, which is this one. And again, you're going to get some practice towards the end of this, and then we'll kind of move on. All right, so I want you to have a periodic table. We're going to, you can use your periodic table, but if you use the one from your reference packet, it might get a little messy on it. So I do want you to kind of make sure you take some time and do this. All right, so we have 4 orientations that we need to account for, or 4 orbitals that we need to account for. We have the S, we have the P, we have the D, and we have the F. All right, so for right now, I'm going to draw, let me back out and get the right color. All right. So I'm actually going to move helium is right here. And so this entire box represents our S. All right. So just to kind of reference it, this would be 1. This would be 1s, 2s, 3s, 4s, 5s, 6s, 7s. All right. Now, let's come over to our P. P is going to be this group of elements right here. Now, for P, let me go back to that. Notice that there are 6 blocks. So this would be P1, P2, P3, P4, P5, P6. And then let's get our D orbital. D is represented by this group of elements right here. Now, I'm going to fix something because notice you have this little blank gap right here, and we have this right here. Technically, these two are part of D. Now, something special happens in D that that we don't see in the other ones. D actually fills in the layer, the quantum level below. So this is actually 3D. This is 4D. This is 5D. And this is 6D. And remember that number 71 is part of D, and number 103 is part of D. So let me go back and kind of, before I move on to the next thing, and just refresh our memory. So remember, this is energy level 1, energy level 2, 3, 4, 5, 6, 7. So notice when you're on the 4th energy level, you're actually going to fill the 3D first. That's how 3 can hold up to 18. And then when you're in the 5th energy level, you would be filling 4D, and so on. Now, getting to our last one, which is F. Oh, before I move on, looking at this, so talking about that we had 5 orientations. So 10 electrons total. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. And then moving on, we're going to go ahead and look at our F. So this grouping of elements down here is our F. Now, just like in D we go one level up, F goes 2 levels up. So notice that these 2 levels would be on the 6th and 7th period, but when we fill it, this one is going to be 4F, and this one's going to be 5F. And that's why, when you go back a couple of slides back, that's why periods 4 and 5 can both hold 32 electrons, whereas periods 6 and 7, 6 can hold up to 18, and 7 can only hold 8. So, when we looked at 7 can only hold 8, we have 1, 2, 3, 4, 5, 6, 7, 8. That's actually in the 7th quantum level. So, all right. So now let's put this into some practice. So you should have a copy of these sheets on Google Classroom. If not, you can draw the little box. But I'm going to try to make sure that we have these sheets available for you, and I will, you can print them out and do this. So we're going to talk about the different types of electron configurations. So a regular order configuration. All right. So on this one, I'm going to do this one with you, and then I'm going to give you opportunity to pause video and practice it on the other ones. So what I would like for you to do right now is go ahead and find arsenic on the periodic table. We're looking for element AS. All right. So now, to show you how to use this, there are other methods to doing this. This is just the method that I find the easiest, especially for those that are just learning. There are some other methods to do this, but this is the easiest way. So we're going to fill using Aufbau, Pauli, and Hunt. All right. So arsenic is in 1, 2, 3, 4. Arsenic is in the 4th period. So that means that the first 3 periods are completely full, or the first 3 energy levels are completely full. So that means that we have 1s2 is full because hydrogen and helium are smaller than arsenic. 2s2 is full. So we've gone past beryllium. Now we're looking at the P's, so we're past neon, so that means that 2p6 is done. In the 3rd period, we have 3s2 and 3p6. And then you're going to say, wait, what about 3D? Well, we're going to actually fill 3D when we get on the 4th energy level. So arsenic is over here. So we have 4s1, 4s2. And then what comes next? This is 3D. So we go all the way through D, D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. So we're going to say 3, D10. All right. Now we are to the P section here. So P1, P2, P3. So this would be 4P3. All right. So, looking at this real quick, what you see is this is our regular order configuration. Now, I'm going to underline one little area that should kind of stand out as something that's a little bit different. We see this 3D10, and it comes after 4S. If we were to do something called the expected order, if it was expected order, we would drop the D in between the S and the P on 3. All right. Very rarely do you ever do expected order. I actually find expected order to be a little bit confusing because then you're not filling in order of energy, you're filling in order of quantum number. And so most textbooks tend to only use regular order. They'll tell you about expected order, but they don't have you do it very often. All right, now let's get to the orbital notation. All right, orbital notation is just a way to illustrate so it's more of a drawing of what we just did here. And I've showed it to you before, but this one we have to remember about the different numbers of orientations. So remember that S only has one orientation, P has 3 orientations, D has 5 orientations, and F has 7 orientations. All right, so on these, we tend not to do orbital notation past number 4. I don't have you draw these. In your part, what you're going to have to be able to do is recognize the pictures. You're not going to have to actually draw these other than in class today for practice. You're going to have to be able to recognize by looking at the orbital notation what element is it. All right, so we're going to fill according to Aufbau first, lowest to high. So we have our 1s, we have 2 electrons. All right, in 2s, we have 2 electrons. We have 2p, 1, 2, 3 orientations. So each block, each blank represents an orientation. This would be the X, the Y, the Z. All right, and we have 6. So we have 1, 2, 3. And I'm filling them like that because of Hund. 1, 2, 3. So there's my 6 electrons there. Now, here we jump to 3s. And so we have 1, 2. And then we have 3p. Which we have 1, 2, 3. And it looks like I'm going to run out of room. And then 4s. Sometimes I'll draw little lines to just separate these, and that's all I'm doing right there. So we have 4s, that's 1, 4s2, and then 3d, and because I'm running out of room, I'm going to kind of do these a little bit smaller. 2, 3, 4, 5. That's my 3d, and it's 10, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the last thing we have, which would be right next to it, or we could start a new line underneath, would be my 4p. 4p is going to have 3 blanks. So we have 1, 2, 3. Now, so talking about this, Aufbau says that I have to fill from lowest to highest, so I start with 1s and I go up to my highest energy level. Pauli says that if two electrons occupy the same sublevel, same orbital, they have to have opposite spins. Hund's rule says that if you basically you're going to fill an equal energy level in the same direction before you start filling the opposite directions. So that's why this one has three up arrows rather than an up, a down, and an up. All right. Now, so that's our orbital notation and our regular order configuration. All right. So noble gas configuration is going to be a little bit different. Basically, all we do is we look at, for noble gas configuration, we're only looking at the outermost electrons. So it actually makes things a little bit easier. So all I have to do is look at what period is filled, what's the last period filled completely. And so notice that, and I'm going to do this in a different color so that you can kind of see what's going on here. All right, so if we look, let's not use green because I've already used green. Let's use blue. If we look all the way up to here, everything is completely full. Now, if we just take this information, that would actually represent argon because we have 1s2, 2s2, 2p6, 3s2, 3p6. So that is argon. So what I'm going to do for noble gas configuration is I'm going to put argon in brackets. Now, for noble gas configuration, all I do is look at what's left over, and I write that. 4s2, 3d10, 4p3. And that's it. All right. Now for valence shell configuration, remember what a valence shell is? The valence shell is the outermost electron. So all we're going to write is what's on the outermost shell. Valence shell will always just be the S and P of the outermost shell. So that is 4s2, 4p3, and then valence shell, we have 2 plus 3 electrons, so we have, valence shell is going to be 2-3, and that gives us 5 electrons in the valence shell. All right. And then the Lewis dot diagram, this is real simple. This is going to lead into what we're doing next. Lewis dot diagram, we take the symbol, and since we have 5 electrons around it, we're going to go 1, 2, 3, 4, 5. Fill in a clockwise order, starting with the first 4, and then start doubling them up as you go. You'll never have more than 8 electrons in a dot structure. All right, so what I want you to do now is I want you to go ahead and pause the video, and I want you to do potassium next. So you're going to go ahead and do potassium, and then you can start the video and check yourself. What I'll do is I'll do a segment for just showing regular order, then orbital notation, and so on. But hopefully you'll get this as you do more practice with them and go from there. All right, so I'm really only requiring you to be able to do 3 things: regular order, orbital notation, noble gas. This bottom part is kind of extra, just so that you can kind of understand what we're looking at with these. All right, so starting this, looking at potassium, this is the electron configuration you should have gotten. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All right, So the way that I got that is I first located potassium on my periodic table, and then I figured out where it is, and I just counted 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, 6. There's my 2p6, 3s1, 3s2, p1, p2, p3, p4, p5, p6, and then I have my 4s1. All right. For orbital notation, what you would have ended up is a illustration that looks similar to this. The key thing is everything is full up to 3p6, so you're going to draw it just like that, and then you get to 4s1, and you have s orbital only has one orientation, so we draw that, and then it is one arrow, an up arrow. All right. For noble gas configuration, notice that argon is the noble gas on the period above it. So that's going to incorporate everything all the way up to 3p6, just like we did for arsenic prior. All right. And then the only thing extra is the 4s1. So from here, I'm going to go ahead and just do that. So our valence shell is 4s1. We have one electron in the valence shell, and number of valence shell electrons, we have one electron, and then our Lewis dot diagram for potassium would be K with one dot. All right. Any questions? Well, sorry, you can't ask the questions directly. If you have any questions, post them in the comment section of this activity, and I will get back with you through the comment section myself, or you can email me. All right. I do want you to go ahead and do this for barium and xenon. For xenon, when you get to orbital notation for xenon, do what's called a noble gas configuration. For both xenon and barium. All right. Basically, what you're going to do is you only show it like an noble gas. I don't want you to have to write every one of these arrows because xenon is in the 5th period and barium's in the 6th period. That could get very cumbersome drawing an orbital notation for that. So you don't have to do a full one for that. You can check your answers. I'm going to go ahead and just fill in the answers. I'm not going to do an explanation on these. If you need the explanation, go back to the previous ones and see, and just kind of go from there. So pause the video, and I want you to do a regular order, a orbital notation, noble gas, and valence for both barium and xenon. And you can pick other elements and try and just ask. You can look these up afterwards, and it'll kind of explain. Just know that sometimes when you look them up, it's going to give you expected order, so it'll move the D's and the F's in the place where they belong. I won't ask you to do a lot with F's. I will probably show one example later on with an F if you need it. There might be one or two in the homework, but on the test, it doesn't ever go that far. All right, so again, pause the video, try these two on your own, and then go from there. All right, so these are the answers for barium. Again, this is what I was meaning by a condensed orbital notation where we only showed the valence electrons for it. So we only showed the 6s2 on this one. All right, for xenon, notice that xenon is a noble gas, so it's going to have a full valence shell, so the regular configuration would look as it does on the screen. For the orbital notation, again, you don't have to draw the full orbital notation, just start with the noble gas on the previous energy level. So in this case, it'd be krypton. And then we would just show whatever's left after that. So 5s2, 4d10, 5p6. Now, one of the things that I want to point out is this is the first time you've ever had to do a noble gas, do an orbital diagram for a D. Remember that D has 5 orientations, so you have 5 blanks with sets of electrons, so 10 total electrons. Same thing with P, it has 3 orientations, so 3 different blanks. Then come in a noble gas configuration, you just put what's going to appear after krypton. So all the electrons, we have to account for the electrons after krypton. And then valence shell is just the outer shell. Outer shell will always only be S and P electrons. So we have 5s2, 5p6. So the valence shell is a 2 and a 6, 8 total electrons. And so we have a full outer shell for xenon. All right. That concludes the lesson today. I will also make notes of what homework, what questions you should be able to do in the homework for Chem 101 and go from there. I will be posting these 2 sheets along with the assignment for you to do as part of your notes. Again, I do want you to take notes during the video. You may have to go back and watch the video a couple of times. Don't have to take everything down. I'm not going to post a PDF of this one because whenever I try to do the PDF for this one, it comes out funky. So you won't be able to see all the writing that I did in the notes. But just kind of go from there and we'll see. If you have questions, post them in the comments section and I will respond to those questions. Okay, for your homework in Chem 101, I want you to do, we've already done questions 1 through 6, so you're going to do questions, you can skip question 7 for now. For now, you will come back to it later. And then I want you to do questions 8 through 11. Okay. I'm going to tell you that pay close attention to number 10. Number 10 is a special case. Pay attention to what's happening with the pay attention to what's happening with the S and D of that level. Some other things that you'll notice in the homework, that it talks about ground state. So don't stress about not being able to get the worksheets. I'm going to work on getting you guys the worksheets. And it'll say things like ground state, or it'll say neutral. They don't want you to steal any of their stuff. Like we bought the program, but we can't even download it on our computers. So that may be my problem, but I'm going to try to screenshot them and stick them in there for you guys. All right, ground rate, ground state, and neutral. That's just the regular order. But I want you to tell me which problems are, because whatever problems you're having, other parents are having those problems. And if I can troubleshoot it, I can it's regular order. You know, because we don't know how long we're going to be doing configuration. I know, because the governor said yesterday he's probably going to keep us locked down until the 30th of April, and I'm like, really? So just kind of pay attention to those. Now, you may be able to move forward in this. I'm going to post another video. It'll either be later today or tomorrow. It starts going into ions, the electron configuration for ions. Just remember, for a positive ion, you're losing 1 electron. So whatever losing one or more electrons. So you would be removing electrons from that, so just deducting the numbers. Um, and then for a cation, an anion, a negative ion, you would be adding extra electrons, so you would have to go forward. So just kind of go from there. This is your homework. I'm going to post those other pages along with this.